Hello, in this video we are solving example to find the impulse response of discrete time LTI system using Z transform. And example is find the impulse response of discrete time LTI system described by following difference equation. Equation is y of n minus 3y of n minus 1 minus 4y of n minus 2 is equal to x of n plus twice x of n minus 1. So this is the difference equation. Now what do you mean by impulse response? Impulse response is nothing but h of n. The response of the discrete time LTI system when input is impulse signal, that is delta n. So this is nothing but first we have to find h of z. H of z is equal to y of z upon x of z, and its inverse z transform is nothing but h of n. So impulse response of discrete time LTI system is h of n. The same question can be asked like this: find the transfer function of discrete time LTI system described by following difference equation and plot pole zero plot. So transfer function is nothing but h of z, which is equal to y of z upon x of z. So this ratio y of z upon x of z we can get by taking the z transform of this difference equation. Once you get this h of z, we can plot pole zero plot. Poles are nothing but roots of denominator polynomial of h of z, and zeros are nothing but roots of numerator polynomial of h of z. And the impulse response is nothing but inverse z transform of this h of z. Let's solve and find the impulse response and transfer function also. Solution: this is our difference equation. So to get the transfer function, first we have to find the transfer function. For that, apply z transform of above equation. Now here in this case, there is a y of n minus 1, y of n minus 2, x of n, x of n minus 1. So here we can apply time shifting property of Z transform, but here initial conditions are not given. That means we are assuming all the initial conditions are 0, and we can take the Z transform easily. Z transform of y of n minus Z transform of this second term 3y of n minus 1 minus 4y of n minus 2, then Z transform of x of n, Z transform of 2, Z transform of 2 we are taking outside constant, Z transform of x of n minus 1. Now while applying Z transform, we can remember this time shifting property. Y of n minus 1 is equal to Z raised to minus 1 y of z. When for y of n minus 2, Z raised to minus 2 y of z. So like this we can continue to get the Z transform. Apply Z transform. Y of n minus 2 is Z raised to minus 2 y of z. Apply Z transform. Y of n, Z transform y of z. 3 we are taking outside, and Z transform y of n minus 1 is Z raised to minus 1 y of z. 4 here constant take outside, and y of n minus 2 Z transform is Z raised to minus 2 y of z is equal to Z transform of x of n is x of z to Z raised to minus 1 x of z. Now this is the Z transform. Now take y of z common here. Here take x of z common, because for transfer function we want ratio of y of z upon x of z. So y of z common we are taking from this three terms. So 1 minus 3z raised to minus 1 minus 4z raised to minus 2. And here x of z take common, 1 plus 2z raised to minus 1. Now take the ratio of y of z upon x of z. So x of z come to the left side, and this bracket term will come to the right side. So y of z upon x of z is equal to 1 minus 2z raised to minus 1 divided by 1 minus 3z raised to minus 1 minus 4z raised to minus 2. And this is nothing but your transfer function h of z, ratio of y of z upon x of z. So when there is a question like find transfer function, you have to do up to this. Now plot pole 0 plot. So for that, this is our h of z. We have to find the roots of numerator polynomial and roots of denominator polynomial. So first I will take z raised to minus 2 common so that we will get the positive power of z. Otherwise you can keep as it is and find the roots. So z raised to minus 2 common. So here z raised to 2 minus 3 z raised to 1 minus 4. Now this z raised to minus 2 will take in the numerator. So it becomes z raised to 2. So z raised to 2 plus 2 z raised to minus 1. So this is numerator polynomial. This is denominator polynomial. Find the roots. Numerator polynomial. Z will take common. Z plus 2. Denominator polynomial. Roots are 4 and minus 1. So I will write z minus 4, z plus 1. So roots of numerator polynomial are nothing but zeros. And roots of denominator polynomial are nothing but poles. So we'll plot pole 0 plot. This is our h of z. This is the z domain, real axis, imaginary axis, and this is unit circle whose radius is 1. Now zeros are nothing but z is equal to 0 and z is equal to minus 2. Poles are nothing but z is equal to 4 and z plus 1, that is z plus 1 is equal to 0 means z is equal to minus 1. So these are poles, these are zeros. For zeros, the symbol is circle. So z is equal to 0 point is here. This is one of the 0 and z is equal to minus 2. This is another 0. Now poles are at z is equal to minus 1. Symbol used is this cross sign. And z is equal to 4. This is another 4. So this is our pole 0 plot. Now we'll find impulse response. For that impulse response, we have to find inverse of this h of z. Impulse response is nothing but h of n. So we'll do that. This is our h of z. Now always whenever you are applying inverse z transform, we have to find the z transform, inverse z transform. For partial fraction, we have to apply h of z upon z. So this z will take to the LHS, h of z upon z, z plus 2, z minus 4, z plus 1. Here you can apply partial fraction method to find the inverse z transform. Always remember, for partial fraction you have to take h of z upon z. So a z minus 4 plus b z plus 1. Find a and b. H of z upon z. Denominator is z minus into z minus 4. Put this h of z upon z is z plus 2, z minus 4, z plus 1 into z minus 4 at z is equal to 4. So this z minus 4 get cancelled. Z is equal to 4. Put it here and you will get 6 by 5. Similarly, find b. B is h of z upon z into denominator z plus 1 at z is equal to minus 1. H of z upon z is this term. Now z plus 1 get cancelled and put z is equal to minus 1 here and you will get minus 1 by 5. So a is 6 by 5, b is minus 1 by 5. Now we'll put these values into h of z upon z, a and b values 6 by 5 minus 1 by 5. Now this z will take to the RHS to find the inverse of h of z. So h of z is equal to 6 by 5 z upon z minus 4 minus 1 by 5 z upon z plus 1. Now apply inverse z transform to get h of n. Inverse z transform, we need to remember a raised to n u of n, its z transform is z upon z minus a, ROC mod z greater than a. Z upon z minus a, its inverse is a raised to n u of n. So that we will apply here z upon z minus a. So a is 4 here. So h of n is equal to 6 by 5 as it is. A is 4. So 4 raised to n u of n minus 1 by 5 as it is. Z upon z plus 1 is here. So z upon z minus 1. Then only we can write z plus 1. So z upon z minus 1. So A is minus 1. That's why minus 1 raised to n u of n. And this is our h of n, impulse response. So here what we did, the difference equation is given, then we calculated h of z, that is the transfer function. Then we plot pole zero plot. Pole zero plot is nothing but roots of numerator polynomial and roots of denominator polynomial of h of z. Once you get h of z, then find the inverse to obtain h of n, impulse response. And whenever you are applying partial fraction to get the h of n, remember partial fraction we are applying for h of z upon z. We all know that. So this is the way how you can find impulse response of discrete time LTI system from difference equation. Thank you.